Our next talk is Breaking Decompilers, and it's my pleasure to announce our next speaker, Jordan Wiens, one of the co-founders of Vector35, the company behind the reverse engineering platform, Binary Ninja. Please put your hands together for Jordan Wiens.
Thank you. So I have the coveted spot right after lunch where everyone has lots of energy and is not falling asleep, right? We'll see if that works. Okay, so the title of this talk is Breaking Decompilers. The subtitle is How to Make My Life Difficult. I'm Jordan, that's my family, that's my product that we make. The company is Vector35, we make Binary Ninja, it's a decompiler. This is how I make sure everyone's awake. So I know you just ate and everyone's tired, so I want everyone who has written any C at any point in their life to raise their hand. Okay, keep up, real high. Okay, now, who has used a debugger? Keep your hands up or raise your hand, there we go. Who has used a decompiler? Hexrays, Ghidra, similar ones. Who has written a plugin for a decompiler? A few less. Oh, I need to talk to all you people afterwards. Who's written a decompiler? I know there's a couple, yeah. I know a couple people in here. Get to raise your hand for that one. Good work. All right, we'll talk more for those of you afterwards. Okay, so that helps me know where we're all at. Here's the goals for this talk. I want you to understand more about how compilers work, how decompilers work, and give you a lot of ideas of how to break them. Right? You should have a bunch of examples that will show you how to do that, but more importantly, I'm going to give you some ideas of things to look at, ideas to go after, and how you can think about what makes them useful and what doesn't. We're not going to be talking about dynamic analysis. We will not be examining debuggers. We're just talking about static disassemblers, decompilers, and this is not an exhaustive list. There are many more things that can be done to break these tools. Trust me, it's an infinite list of things that can be done, but we're going to have a whole bunch of them that we'll talk about and explain the difference. Okay, so first we're going to talk about why decompilers are actually impossible. Well, then we're going to talk about how they work at all, and then we're going to go break some stuff, right? That's our goal. So first, why are decompilers impossible? Okay, so here's my brief colloquial explanation, casual explanation for why a decompiler is impossible to do perfectly. If I write source code and I compile a binary and I strip out all the debug symbols, you don't know what my names were. You don't know the names of my variables. There's information that's lost, provably lost. Comments are gone when you compile them down, right? So this is, I think, pretty intuitive. If you've ever looked in a debugger, like you understand this, right? But this expands to more things as well. There's a lot more things like that. Here's another example. Who wants to take a guess and tell me everything this code could possibly do? Does anyone want to take a guess what this code could possibly do? Anything. That's exactly the answer. This code can absolutely do anything because it takes user input and then it runs it. It literally will just do whatever you do. So if you look at this program in advance, you cannot tell me everything it can possibly do because you don't know what it can possibly do. Right? It takes input, there's state, there's context, there's things outside of just this code that will influence what it does and how it behaves. So you don't actually know that. Now, I'm not an academic. I want to be very clear. I do not have a formal background in program analysis. I am a practitioner. I make a tool to help reverse engineers. I'm also the worst reverse engineer and the worst developer on my team. That's why I get to give talks, because I'm good at talking, but I'm less good at coding. So everyone else is better than me and smarter than me. But this is a useful concept here. Rice's theorem is this idea in computer science that basically anything that's not a trivial property of program analysis is impossible, right? You've probably all heard of the halting problem, right? Halting problem? Anyone know that? Raise your hands. Come on. I know more people have heard about the halting problem. The halting problem states you can't tell me by just looking at a piece of code if it will necessarily quit. You can't tell me if it even stops. Such a basic property of whether the program will ever quit is actually impossible in the generic case. Now, conveniently enough, most of the time we can. There's a lot of ways that we can make it work, but officially we can't. Okay, so this is just a real quick animation of Binary Ninja finding some code in a binary. This is our equivalent to IDA's little scrub bar that shows you strings and data. But the idea is that we're looking at things that could be strings. We're looking at functions. As it's trying to identify where all the code is, it's marking it up. This is actually a really hard problem. This is another one of those unsolvable problems in the generic case. You cannot prove for sure whether any piece of any byte in a file is code or if it's data in the general sense, right? You cannot, for all files, for all situations, you cannot do this. Now, most of the time, you can. Sometimes you have really good indications. When you open up a file, there's an entry point. That's where the operating system, the CPU, will begin to execute, and you know there's probably code there. Well, maybe there's other actually things in the loader that will mess with the memory. Maybe it does other things like that, right? So there are still even some asterisks, some caveats, some things there. This is something that I think people who have not written a disassembler or a decompiler don't even understand how difficult this actually is. Trying to just identify what's code and what's not is actually a problem. Okay, so decompilers are impossible in the general sense. But obviously, they're not, because many of you have already used decompilers. We know that. Okay, so how do they work at all? Why do decompilers function, and how do they function? So there's basically 3 steps that every part of a decompiler, every optimization thing it does, it goes into this process, right? We're going to parse some files. We're going to lift. We're going to do some analysis of the machine code instructions, the operations, the opcodes. And then we're going to optimize the results. And then if it works, we give you source code, right? Like that's the goal of a decompiler. What does this look like? What other technology is actually similar here? Anybody want to take a guess? Compilers. Exactly. That's how compilers work. The only difference is instead of lifting, going from the opcodes themselves into this intermediate representation, they go the other way around. They start with the source code, but they still have to parse it. They turn it into an abstract syntax tree. So we're doing the exact same thing that a compiler is doing. We're just doing it in reverse, right? And so each one of these steps, each one of these pieces of the process are what we're going to be attacking. So when we talk about breaking a decompiler, what we're looking for are flaws in each one of these. And we can see, I just asked ChatGPT, because that's apparently the thing you do now, and it told me, how does the binary compiler work in 3 steps? And it gave me those exact 3 steps, because that's generally what they do, right? Okay, so let's talk about briefly parsing. There are certain things that are associated with parsing a file that we're going to analyze. Some of these are going to be specific to some file formats. Some of these depend if it's a firmware or if it's a raw, it's a part of an operating system. There's going to be different features of each of those. But most often you're going to have some features like this. And again, every one of these is a spot where things can go wrong. It's a spot where you can break stuff. So we'll show some examples of that later. Right? We have Mako, PE-ELF, segments and sections. Not every file format has both. Sometimes you just have one. But there's going to be memory mappings, permissions, so you know what's executable, what's not, what's data. And there may be some extra metadata. Can you trust that metadata? It depends. If you've done malware analysis, the answer is generally no. There's a lot of things that malware will do to lie there. And then relocations. Oh boy, do I hate relocations. Okay, so parsing, step 1. Step 2, lifting. And by lifting, again, we're turning those CPU opcodes up into some intermediate representation. Who knows what hex 90 means most of the time in an opcode? In the back. It's a NOP, exactly. A NOP, right? See, these are the opcodes, and when you've stared at disassembly long enough, you begin to memorize a whole bunch of them. They make sense. But the CPU decodes it, it takes some operation, it acts on it. But the humans, we need to have it abstracted to a higher form. We need to turn it into something else. And so Binary Ninja does that with BNIL, Binary Ninja Intermediate Languages. There's actually 7, 9, too many. There's a lot. We have a whole bunch. P-code is what Ghidra uses under the hood. And then there's microcode. Does anyone know what P-code stands for? It's Ghidra's, but what is it actually? The original research they used a term for P. It's not pseudo, which you might guess. It's not what P stands for. What does the P code stand for? Anybody know? I'll give you a hint. This was the era of Java, when the idea of things being able to move around was really, really useful. Any ideas? Portable. I think I heard it. Somebody said it. Good answer. Very good. Portable code. That's actually what the P in P code from Ghidra stands for. Okay, so I have a whole bunch of other talks or slides you can go look at if you want more details on that, more memes on lifting and whatnot. So that's the second area we're going to break. First, we're going to break the parsing, then we're going to break the lifting, And now we're going to break the optimizing. This is the last step of it, right? And so optimization occurs in the decompiler by taking type information, for example. Maybe we've got signatures, flirt and flare, or warp, or sigkit, or these other libraries and technologies where we can say, oh, I know what that thing is. Maybe it's a thing you're importing. Maybe it's a thing that you've statically compiled. Either way, I can recognize it, and I can apply exact type information, which will dramatically improve your decompilation. Dead code elimination will improve the results if you have a binary that's using opaque predicates, for example, an obfuscation technique that will make a lot of sort of dead code paths. Well, if you have the right optimizations, those just go away. So these are things that you do to make the analysis look better. There was a great talk at Reverse earlier this year by Zion Leonahe Baski. There we go, I got his name right. Got to get it correct. And he talked about the control flow structuring. Right? Because when you write a switch statement in your source code, what that actually turns into in the CPU is a bunch of if-elses or maybe a jump table. There's a bunch of other constructs that it gets turned into. The CPU is going to run, and so turning that back into like the easy-to-read switch statement is something that decompilers will try to do. So that's part of the optimization step. All right, let's talk about what makes a good breakage, right? So I'm going to give a whole bunch of examples here on ways that we can break decompilers, and I want to like make each of them sort of measurable. I want to talk about 3 criteria, which I'm going to say are either good or bad, depending on the example. And it depends on what you're doing as to whether you care about these. So for example, how effective is it? Does this breakage, does this thing that we're going to do to break a decompiler, does it actually stop me from understanding what's going on? If the answer is no, then that's not a very good score, right? So low score here means it's an ineffective way to break the decompiler. It doesn't actually stop me from doing something. If it's a 5, it's very effective. It's very difficult for me to understand what's going on in that binary. Okay, evident. Now this is, I should probably have called it stealthy or something else, but I wanted to do ease for all of these, so I tried really hard to make them all match with ease. So we have, is it effective? Is it evident? In other words, how obvious is it? Is it really obvious that something is going on? This is what I think people oftentimes forget. Because if you can just take something and like put it in VM protect, it's really hard to reverse engineer, right? Like this is very difficult. It makes your life a lot harder. But I know that you're trying to hide something. I know exactly there's something going on here that you don't want me to see, and then maybe I'm willing to invest the time to figure it out because it was very evident. So again, a low score means it's very obvious. It's not effective at being like sort of stealthy here. It's too evident. And if it's a score of 5, that means it's very, very good at remaining hidden. It has a good high score on that. So again, evident, it's kind of backwards, but we'll do as low to high just so that we can add up the numbers to kind of get a sense of where things are at. Okay, finally, effort. How much work as a developer or as somebody who is obfuscating my code is it going to take for me to implement this? Some of these techniques are a real pain, and I don't even implement them in my demo because it's too much work and I don't want to bother with it. And some of them are very easy. Okay, that one's kind of straightforward. One is very easy to implement. Actually, oh, did I do that backwards? I think I did that one backwards. Oh no, that's the problem with changing your slides last minute. That's all right, we're gonna break stuff. So let's actually show some of these techniques and let's break our decompiler. Okay, so this is the source code that I sort of just a real basic, the simplest crack me you could possibly have, right? That we're gonna compare all of these obfuscation techniques against. So we're gonna start with that. We're gonna look and see if you got the correct password, and then here are the overview of the examples that we're gonna show off. We'll look at them in Ghidra, Binary Ninja, and Hexrays, and we'll talk about all of them. If anyone else wants to look at a different decompiler, we could do that too, actually, because we have them all up in Dogbolt. So again, we're gonna break the parsing. We're going to break the lifting, and we're going to break the optimizations. Okay, so break the parsing. Relocations. Relocations are the absolute worst. They take way too much effort, right? This is, oh, here we go. This is, effort is 1. I can fix my bug now, right? Let's see. Effort 1, yeah, okay. I got that one backwards. That's all right. The numbers are there just to make it look scientific when it's not scientific at all. So, relocations. Relocations are involved in linking binaries together, right? When you've got a library, you're calling into that library. The operating system, the loader, is going to put everything into memory, and it's going to fix up the addresses. It's going to say, oh, libc is over here. Oh, user32, that's over here. And so those are usually updated with relocations. There's a couple of different ways different operating systems will do it. And these are a real nightmare because every file format and every architecture does them differently. So ELF doesn't have one way of doing relocations. ELF ARM does relocations one way. ELF MIPS does them another way. Everything has its own ABI and can implement relocations in a really obnoxious way. So this is really effective, especially if you are implementing things on like an embedded platform. You can often find all sorts of weird types of relocations. I didn't implement this one. This is one of the only ones I think on the deck that I did not implement because it's a pain to do and it's a pain to reverse engineer. But I just wanted to complain about it as a compiler developer that even the legitimate ones are actually broken there. Okay. Section shenanigans. And this is one that malware authors will see. Again, we're in the parsing phase, so we're loading our file up, and we're going to find where the memory is supposed to be. Maybe there's some extra information. A lot of file formats will have specific sections with extra details that will tell you things like, oh, here's some init functions that I want you to call before you even call into main. That's useful. You'll often see in CTFs, it's quite common for someone to hide some functionality in an init function. And you won't notice it because you just always go right to main, and you assume that's the first thing that's going to run, but it often isn't. Okay, so this one we've got some source code to, so let's pull up the sections and take a look at it. So you'll see on this one there's a little bit of complication where, no thank you VS Code, I'm good. This actually comes from an example in the Paged Out magazine from Kale Zeta 2, and it's not a new technique even then. It's been documented several other times. But essentially, by messing with the sections, we can get the tools to just completely miss bits of code, and we can get them to run our code before you even see it. So this is actually done here in this create trampoline file. I'm not going to go into all the details. This one involves some modifications of your linker script and using like obfcopy to like modify things, inlining assembly. We're not going to have to do that for most of our examples. So this one I think counts as a little bit more difficult because it is harder to put into your build system and to test things because you've got too many pieces. Things are kind of all over the place. But let's take a look at the results. Oh wait, where is it? Here. Let's go look at the result. So the result is base.elf. Unfortunately, they're all named base.elf, which makes it a little annoying. And we're going to see there's a main function, but you'll notice we didn't see a normal, actually, wait, here, let's switch into here. So we go to the main function, and things look okay, but if we just scroll through here, you'll notice there's something that we missed. There's a backdoor string. Where is that one called? It's called from this function over here. That function has no cross-references. Oh, that's annoying. So maybe it's not called. No, it is. This is absolutely called. But we've messed with the section information, and so it looks like it's not actually called. Now, I can fix this in Binary Ninja because I know that this is a bug we introduced in the last release. So if I actually load the binary up and I load it at 0 instead, and then I look at it, I will actually see, where's the backdoors? I will actually see that cross-reference. I'll see in the init array that there is a call. Where'd it go? So in my backdoor string, puts the strcomp. No, wrong one. Oh, it's not pulling out. All right. This is the problem with doing it live. You never know when you've missed something that you did in your script. So we can actually look at this as well in Dogbolt. This is the other thing I'm going to be using a lot. If you haven't seen it before, how many people have seen the Compiler Explorer in godbolt.org? The Compiler Explorer, and now how many people have seen the Decompiler Explorer? About the same. That just tells me those are the people willing to raise their hands, I think. That's what we've really learned, right? So the Decompiler Explorer is going to be a really convenient way to look at examples across all of the common decompilers. So by default, it's going to show us Anger, Binary Ninja, and Ghidra. You can turn on and off certain ones. Like I'm mostly talking about Anger here, so we can get a little bit more screen real estate. And we can see, for example, where things are referenced from, right? So this is what we're going to use for a couple of these binaries. We're going to see which tools can handle it and which ones can't. And what is interesting is that they'll change over time. So what may have broken in IDA 8.4 may be fixed in IDA 9, and vice versa. Both can happen. All right, so let's go back to this one, because I think I broke that exercise. I'm not sure which one I did with that. All right. This is actually probably the easiest section to build your own, too, right? This is one that I want to point out. This is probably the best way if you want to just break a decompiler in a way that it can't open your file and to be annoying, is you can fuzz the file format, open it up in, get the expected output, and if it still functions, the loader on the operating system is fine with it, and now open it in your tool and try to just dump out the disassembly, dump out the decompilation, and analyze it. That's probably the easiest way to find some really good breaks. And there's a whole bunch of things, again, with section headers, segment headers, with all of the different properties in the file format. Again, whether you've got a Mako, a PE, or an ELF, that's probably the easiest way to do that. So you can do that for all of these, but that one is especially bad. All right, let's go off and break the lifting now. So again, the lifting, this is a really classic one. We've got a couple people, I think, who will read disassembly. What is this one going to do here? What does this code actually do if it's x86 32-bit assembly? Jump to itself, sort of. It's going to jump in the middle, right? Oops. Previous. There we go. So EBFF says jump -1. But it jumped -1 from the end of the instruction, because if you jump 0, it's like a NOP. It's going to go directly into the next instruction, so it would start executing. And what's the C3? The C3 is return, exactly. So this looks like it's going to do some sort of jump, and then it's going to return. If we just do disassembly of these bytes, that's what we're going to get. We're going to think it's going to do some sort of jump, and then it's going to return. And depending on the implementation of our disassembler, that's what's going to happen. It's going to see return, and we're going to stop. And that's what IDA did for a very long time, is it would always just disassemble through and see a jump and then return, and it would say, oh, well, that function's done. I'm going to stop analyzing it. What it actually does is an increment EBX, because that's what FFC3 does. It's one of the weird extra encodings where it does that, because it jumps back into itself, and the FF becomes the beginning of another instruction. So that's a weird thing. Let's take a look at that one and see how that looks here. And this is, I'm cheating a little bit. This is one in Binary Ninja we knew about a lot, and we made sure that it didn't break us from the beginning. So this is important. There's a bunch of concepts in decompilers that are baked into the design and the analysis. So I'm going to tell you also flaws that are designed to break Binary Ninja, because we make assumption other tools don't. But this is one that from the beginning we knew that if we didn't want to be vulnerable to this. And so you can see, for example, there is a, where did it go? The continuation from function main, right? So the actual start of main is up here, and in this case, we've actually got these short jumps in a row that are just being shown to us together. When Hexrays fixed this, they fixed the bug, but only if it is exactly EBFFC3. If it's any other offset, you can still do this, and it will still break. It will still see a C3, and it will return. And so it also doesn't work in 64-bit disassembly, so you can do it there. So let's go ahead and open it up in Dogbolt. Thanks. And we can see, does Ghidra handle it? Ghidra appears to handle it just fine, right? So we've got our main function here. We can still see the password. Binary Ninja's got it there. And then Hexrays, let's go look at the main let's go look for where did the main function? It's just gone. The main function is not there at all. It just doesn't show up, right? So it's cute, but that's also really obvious, right? Again, thinking back to that criteria, is it obvious that you've done something? Yeah, it's extremely obvious that something is broken here. And we can even see when it does the libc main, where you normally would have this pointer to main is just this really extra bizarre, oops, there it is. So yeah, main doesn't actually exist here. It's just gone. Right? And now that can happen too, because we're using an automated script to decompile the binary in one shot. You can probably fix this up. Most of these you can fix in the tool in question. And so that's also really important, is that knowing you can't generally solve these problems, and that's okay, because again, the user can come along and fix it if you know that it's there. All right, so that one, we got IDA with that one. It's an old classic one. Let's go to our next one, right? Oh, and it's worth mentioning, if you want to play along with these, there's a link at the end, but it's on GitHub, and so you can play with all the source as well. Okay, this is one that I particularly don't like, because real code actually does this one, right? Several of these are really obvious, and you know something's trying to mess with you because normal compilers don't do these things, normal output doesn't do that. But you know what you can do is you can just use some CPU vectorized instructions. How many people have reverse engineered some like mem copy and it was like some vector ops? That is the absolute worst, right? So you're not actually abusing any behavior other than the fact that these things are extremely annoying. And they look legitimate, because if you've ever looked at like video games, they're full of this stuff, right? They're doing a bunch of vector operations. They want to be super efficient. If you've got something where speed is really important and you've got a CPU that supports these wide instructions, that can do math on like multiple things. So I asked ChatGPT to write it for me because I'm lazy. And this is the source code it gave me, right? So we've got this vectorized string comparison. So it's just a string comparison function, except we're going to use like wide comparisons. And we're going to check with a mask whether or not we have to keep going. And then actually it's got some other longer behavior which is just going to call through to strcomp, so that's a little bit of a hint. So thankfully, in this particular implementation, we can see it there, right? But now, before we had our password comparison, we could see it was a strcomp before. Obviously, with the name being here, we know it's going to be understandable, but once we strip that off, that's gone. So let's go ahead and open that one up. And let's see what that one looks like. All right, so we've got some sort of comparison. Again, let's just pretend this is gibberish. You don't know what it is. You might be able to figure that out, like in this case, but we could obfuscate the other parts of it. Let's actually look at that function. And it's just as gross as you'd expect. Like, that's not fun. No one wants to look at that, again, except for that strcomp in there, but we could certainly remove that. That was just kind of a backup put in by the ChatGPT thing. All right, and now let's go to dogbolt. Let's see what we've got there. I did the wrong hotkey. Yeah, that's cute. It does that. Too many tabs open. The icon's really cute. I'm not allowed to say who made it, but it was a really good little icon. See, it's like Harry Potter. He has a little lightning bolt in his head. Okay. Let's see. Does Ghidra do any better? Well, sort of. It's interesting. Here's how Ghidra handles this instruction, right? Let me know if you can read it in the back if we need like a bigger font. Ghidra does know how to lift these operations. It understands how to transform into P code the exact behavior of this instruction. So, I mean, sort of. It can handle it, but does it help you as a reverse engineer understand what that does? Is that more understandable than Binary Ninja and IDA? Hexrays both and Binary Ninja both do the same thing, basically. Maybe it does, maybe it doesn't. Kind of depends. Sometimes it's actually worse. One of the things that we debate a lot when we're making things in Binary Ninja, when we're lifting, is we have to decide, do we want to exactly model what the CPU is going to do for that instruction or not? Because Ghidra has done that here, right? They've modeled what that CPU instruction has done, but it's not really adding to our understanding of what happens here. So sometimes you're better off not modeling it. A good example would be like AES instructions. x86 CPUs actually have an AES instruction. You can do a round of AES with a single instruction. You initialize it, and it will do all that for you. That's much better to just show the user AES next instruction, right? That's much more readable and understandable. But if you want to do some kind of program analysis where you're tracking data flow, well, maybe you want to have that modeled. Maybe you actually want to see the full implementation. It's sort of a trade-off. You have to kind of decide what you're going to do. So in this case, Ghidra chose that one. I don't know, I'm curious. Who likes which one? Who prefers the vectorized instructions? Who prefers the explicit listing of the operations? There's no wrong answer, right? And again, depending on what you're doing, one might be better than the other. So completely fine. No judgment there. I'll judge you for other things. Okay. So let me make sure I've got them all. All right, so that was all of our lifting. Great. Now let's break some optimizations. Someone asked me last night and said, okay, you said the talk is called breaking decompilers, but what are you actually breaking? Are you breaking disassemblers or are you breaking decompilers? And some of the things we've just talked about are really just breaking disassemblers. Right? Any binary tool that's going to load an ELF file is going to be broken by some of those shenanigans. It's not really attacking the decompiler itself. So I promise some of it would be targeted towards the decompilers, and this is where we're going to talk about that a little bit more. Okay, so one of the problems that decompilers have to handle is how do you know when a function quits, right? How do you know a function is not going to actually terminate because you want to handle that differently in your decompilation. If somebody calls exit in their application, you want to stop your analysis because after that there might be a bunch of garbage, there's other things, there's noise, you don't want to keep doing that. So you have to handle that. It turns out that both Ghidra and IDA, if you name a function quit, they stop. Doesn't matter if it's actually quit. It doesn't matter if it's just a normal function in the binary. Just use the letters QUIT and they stop. They're happy to just end whatever they're doing. So let's go ahead and look at that one real quick. All right, so we can look at our makefile. Funny thing is GCC also doesn't like to produce these, so this one does get a little bit of a ding in terms of how difficult it is because of that. So I literally use sed to just string replace stop with exit. Sorry, did I say quit earlier? With exit in the binary. So the resulting function will be named exit. Again, I'm not changing the behavior at all. And if we actually look at our source code, we have our function called stop that just prints a line and does nothing else. That's all it does. It just prints a string. And so now let's look at what that one does. Let me close some of these ones. Oh no, did I hit quit instead? I did. All right, well, that's fine. You get to see how good Binary Ninja startup time is. Okay, so let's go and open. Yeah, I know I had a plugin going. I broke it. Okay, so let's look at stop, and let's look at this build. By the way, the build scripts, some of these exist for Linux, some of them exist for Mac OS, and none for Windows just because I'm lazy and it was easier to set that up on my machine without it. Okay, so Binary Ninja, we have the function called exit, which just returns puts instead of printf. Sure, it'll optimize that away. That's fine. And we can see we call exit, but then we keep doing everything else. All right? Let's see what these tools do. All right. Actually, you know what? I haven't looked at Anger. I'm curious what Anger does. Anger does the right thing. I thought they might. There we go. So Anger does the right thing. We called a function called exit, but we can see what that function does. It just prints something, it keeps going. Binary Ninja does the same thing. Call exit, then keep going. Let's look at Ghidra. Subroutine does not return x. Okay, well, there used to be more code there. And let's look at, where's hexrays? What's main in here? Oh, no, that was it. Yeah, that was main. Okay, there we go. So Ghidra and hexrays both just really want to know if it's stopping or not, and so they'll trust you. Just trust me, bro. It said it was exit, so it must be exit, right? Now, the right way to do this is to actually make sure, one, if it's statically compiled, if I have a statically compiled libc, I should have some sort of signature library. I should doing some sort of matching of that function, and then I can apply the annotation, the extra information, that this function actually quits, does not return. Now, you can fix this, right? I actually don't know in Ghidra the particular method for it, but like in Binary Ninja, I can edit the function properties, and I can say can return, right? By default, we got it right. But say I wanted to mimic that same behavior in Binary Ninja, I can set that there, right? You can turn that on and off. I'm sure there are ways you can fix this in Ghidra and in IDA if you know where to go looking through them. But the key thing here is if you don't notice this, like you think you're done, like you think your program's ended. So I like the sneaky one. That's a fun one. All right. And again, at that point, we're applying our attack against the, oh, it's got a million. Every time I navigated, it updated the history. Okay. We're applying our attack against the optimizations because it's the compiler now, the decompiler now, which is trying to apply type information. It's trying to infer what the type of something is, whether something returns or not, because that improves the decompilation. And if you don't do that, you're little better than a disassembler. And so this is where we can really start to have some fun, is by breaking these. Okay, UPX is kind of dumb. I don't even know if I'm going to open this up because I think many people, if you've reverse engineered, you've seen what UPX looks like, right? Any packed system will do this. You open up the binary, and there's a little decompression stub at the top, and then there's a bunch of data. And that's annoying to reverse engineer, unless you just run it, or you have an unpacker, or you use unpack.me or something like that that's designed to do that. That stops your analysis, especially if you've got your own custom obfuscation. But it's pretty obvious, right? So I think it's Oh, see, that one's wrong. That should be lower evidence scores. Like I told you, those numbers are completely made up. They're just to make it seem more scientific. So that one's actually wrong. But yeah, so you can just UPX the binary. Again, though, you could also VM protect. You could also use one of these other, use some of these other obfuscation systems that just obfuscate the whole binary by packing it and encrypting it. That's a lie. We're not going to demo that. Okay. The shellcode compiler. The shellcode compiler is been built into Binary Ninja since we launched like 10 years ago, and very few people even knew about it. The docs are actually online if you want to look it up, scc.binary.ninja. And it has a whole bunch of neat features that very few people are aware of, although some of these, by the way, are lies. We never actually finished all the functionality, so the documentation is not to be trusted. But the source is open now, so you can go find it yourself. If you look on our GitHub, Vector 35, I think it's just SCC. You can go look at it, and you can actually see which features are actually implemented or not. And so you can find it yourself. But there's all sorts of really like weird things here. You can set oh yeah, this one doesn't work. That one definitely doesn't work. You can tell it to polymorph, where it'll randomly insert different instructions each time. You can set the stack to grow upward. If you want to have your stack not grow down, but grow up, sure, you can do that. Now, push and pop aren't going to work, right? So all your stack operations are like moves and subs and adds to the stack pointer. And speaking to the stack pointer, you can set your own stack pointer. Maybe you want to use a different register. Now, like these are specific examples that this tool happens to implement, but there's a lot of other things that can do this. You can modify Clang. There's a lot of people who've built obfuscating compilers. I talked to Fred earlier, and he was mentioning they've done this before too, right? There's a lot of ways that you can do this. Tigris is another tool that gets done. And anytime you implement your own compiler, the results are probably going to be pretty bad for the tools, right? All of these decompilers are sort of built around testing real compiler results, and so you give them one they haven't seen before, and it often ends badly. So let's look at that. There's the docs. We already looked at that. Let's go look at one that I compiled with SCC. So Anger just gave up. It exceeded the time limit, but it did so immediately, so I think that error is a lie. I don't know what happened to Anger, but it died. And just for reference, let's look real quick. Here was the source code. Again, it's the same source code we've been basically using the entire time. We built it with SCC, and then here's the actual, oh, actually, it's a make script. So most of it's just finding where SCC is installed on your box, basically. This will build a Mako and an elf. And then, yeah, we're going to call it with this. Now, again, because this hasn't been updated in forever, some of these obfuscations only work on x86, so it is a little lame in that regard. But that was it. I just told it to use RBX as the stack register, and that was it. Nothing else. And I gave it the same source. So let's now see what Binary Ninja did. Okay, Binary Ninja did fine, right? We've got, this is a little weird, like we don't have a for loop, we have this while loop on a condition, and we're doing like a string comparison in here, but we can see we've got a syscall. This jump looks a little weird, that's not great, so there's a little bit of shenanigans going on there. Ghidra, there's a local variable, and that's nope, I don't know what's happening there, but all right, we've got our loop is sort of there, and let's go look at Hexrays. Let's see, was it starter? Let's see, what was this one? This is just entry point. There's no main. So yeah, where was? Oh, there we go. Start. All right. And there's Hexrays. I don't know what Hexrays is doing. And I want to like be very clear, by the way. I have a lot of respect for both Ghidra and Hexrays. And Hexrays in particular has fantastic decompilation most of the time, right? It really is heavily optimized to produce good decompilation for normal compilers. This is an example, though, what happens when it can't pattern match on that compiler behavior and instead has to fall back to heuristics. I don't know what it does, but that's very not right. Like, there's a loop in here. Why is there no loop in here, right? So again, and there's plenty of ways you can break other tools. All right, let's keep going quickly. This is one I'm gonna make sure I break Binary Ninja really badly too, just Binary Ninja to be fair. So Binary Ninja uses data flow to do a bunch of analysis. I mentioned earlier opaque predicates, where you've got like multiple paths, but there's really only one path. Only one is real, and the other ones look real, and so your disassembly and your analysis go off to analyze garbage. Binary Ninja will try to optimize that away. And it works really well, actually, for some of these opaque predicates. But the flip side of that is Binary Ninja trusts the memory permissions. So if I have this file, for example, where I have this read-only variable. So check var is 0. It must be 0 as the file is compiled, right? But then I actually, under init, I just do some shenanigans, and I make that memory writable, and I change that value, and I make it 1, and then I go back and continue execution. Well, when I get into main is going to see is check var equal to 0. Nope, it's not, and it's going to keep going when I actually run this, right? But Binary Ninja isn't able to reason multi-procedural and say, oh, this thing changed memory, changed the global variable. That variable is now temporarily in a writable area. And so when I open this one, I have a link yet. There we go. When I open this one in all the tools, Binary Ninja is going to say, oh, wait, where'd that go? That's it. That's your whole function, right? Because it saw that check, and it knew that check couldn't possibly be true, and it exited early and said, nope, we're done. That one doesn't actually exist. And the other tools all do fine. So we can see the memory mapping, and you can see the code. The memory mapping is there. We can see that code. But over here in Ghidra, we see this check, and we happily go right on through it. In Hextrace, we're going to see this check, and we're going to happily go on right through it, right? So totally fine with those two. Now, I have to show you how to fix it, because I am a Binary Ninja developer. So there's a couple ways we can fix that really easily. We can open with options, and we can actually disable that feature. It's just an optimization feature that we can turn off. But again, you kind of have to know to do it. So I can keep unreachable code branches, and now we'll actually see the code is there. We see this call to exit. The if gets even compiled out. Wait, is this the right one? No, that's stop. Hold on, that's the wrong binary. I should have seen if somebody caught me before I did it. All right. Which one is this again? Data flow. No, there's main. Okay. So there, it's gone, right? We don't see it, it's exiting early, but now if I open with options and I turn off that setting, now we see the whole code, right? So there is a setting, there's a feature, but you have to know to look for it. So I told you I wasn't just going to make fun of the other tools and pick on them. So there we go. Okay. Do a quick bonus round of breaking LLMs. Totally off topic, I didn't promise this. But much related to how both Ghidra and IDA, remember, they trusted the word exit, the string exit. And they're like, that thing must exit. Well, you can really do the same thing with LLMs. So I think we're going to see a lot of fun as you see more things like MCPs. And we even have our own tool called Psychic that's actually really useful for legitimate normal stuff because it's really, really nice. But if you have malware now that starts really lying subtly, you can really do some shenanigans. There's a video here because this was a live CTF challenge that we ran for the DEF CON qualification round. And my goal for building this challenge was specifically to do exactly that. I just wanted to mess with people who were using AI. And then I couldn't get AI to solve it anyways. So I didn't mess with them at all. I left the normal strings in, and AI still couldn't solve it. So we're not there yet for that one anyways. But keep an eye out for that, because I think that's going to be really fun the more people start doing that. Okay, so here's a bunch of lies. I told you earlier those numbers are fake. Give it a veneer of official scientific results. I don't think they're all that super useful. But I do think it's useful to think about, why are you trying to break a tool? And is it really important to you that you're subtle? Do you not want somebody to notice that you've broken their analysis? Or are you totally fine with them knowing it? You're a game company selling some DRM piece of video game. You don't want to have someone cheat at your game. You're fine if they know you're doing something tricky or complicated, and you want to obfuscate it as much as possible, right? So there's just different priorities. If you're building an implant that's going to run as a backdoor in somebody's box, you really want to make that look like normal code, and you still want to hide that behavior, right? So depending on your goals, you're going to have very different features that you would take advantage of. Okay. Oh yeah, that was part of the conclusion there. So my final point here is decompilers are easy to break. I think they're hard to make. It's a terrible business to be in. I don't recommend it. But I'm happy to take any questions. I think I have. There's the slides. There's some credits here too, tools that I used. But yeah, I'll leave that up if anybody wants to get just that GitHub URL has the updated slides. So, all right. Any questions? Yes. Yes. The dead code analysis was done in an ELF. The same technique would apply in every platform, however.
No, because the thing is, Hexrace, at least for Mark 4, also has the same problem. Only there's like a variable. Basically, your example, Hexrace will not see it unless you fix that.
In fact, actually, somebody mentioned that to me recently because we've just been updated our DILD shared cache analysis, and I think somebody specifically mentioned that Hexrace does the same thing. And the problem is, if you don't do that, your default analysis in many cases is much worse. So this is one of those like danged if you do and danged if you don't. Like you have to kind of support both options. It is also worth mentioning that if I actually look at that comparison here. This check var. The other thing I could do in Binary Ninja is I can mark it as volatile, right? I can tag it as volatile, or I can tag it as const, and that will inform the analysis. So I can also do that. I can also change the memory permissions, as you were saying. So we actually have 3 different ways to improve that. But again, you have to know it. And yeah, okay. I feel a little better that Hexrace gets that wrong in some contexts too. I'll change my demo to use a Mako next time. Yeah. Anybody else?
Excuse me. A long time ago, I don't know if I don't know if they still implement this in present, but if I remember correctly, they had a bounty program that if anyone can crash IDA, they will pay the money. So my question is that, have you ever encountered any examples that not these examples, they only prevent the analyzer, the reverser to analyze the code, but some extreme case where
actually crashes the whole program.
Yes.
Absolutely. And I actually should have had that in here. That's a great point. You can 100% crash most of these tools too. Maybe not Ghidorah as easily because it's Java. You could probably get it to or something. But it's would you know the difference? It's slow enough? Sorry. But Binary Ninja, for example, we use a lot of Rust. And I think just a few weeks ago or a month ago, there was a Rust assert that crashed the application. It was not a security issue. You couldn't do anything with it, but you could actually cause it to crash fully. Those are pretty easy for us to fix and get them back up and going. But that's absolutely valid. And I'm trying to remember the last time I've seen somebody crashing IDA. I think people have been fuzzing that a fair amount, but these file formats are infinite. They really are. The number of features, trying to track Apple's changes to Mach-O, as Stefan and others will tell you, is a nightmare. They are constantly adding crazy new features to the file format with every release of iOS or Mac OS. And so every one of those is a chance to go break a tool. Even if, first we have to just support it in the first place. Sorry, my machine turned off. And then secondly, there's just going to be bugs in it until they get kind of worked out. So yes, crashing tools is great. You can absolutely do that. The same technique I mentioned for fuzzing sections tends to be useful there. But most of those tend to be either in a specific feature. So like I said, we had a crash in I think it was our PDB parser, maybe, or dwarf support, one of the two recently. And I'm sure there's still ones that IDA has too. Yeah, good point.
And one more thing, in real world scenario, besides exploitation, other products, how often you encounter this crash case? I think someone will try to find flaws in this decompiler, and then they modify their binary to make the decompiler crash. But in real scenario, how often,
I can't think of a time outside of a CTF where somebody has ever reported a flaw that ever caused a crash. And I think the main reason why is, as I was saying earlier, if you're a professional building malicious software, right, you do not want to be caught. So it's far more suspicious to crash a decompiler that's a part of somebody's automated pipeline than it is to be very benign and look normal and have nothing strange happen. So I think there are plenty of people who are capable of it if they wanted to, but it's not a goal for them. And so you see it in capture the flag contests because it's cute and they want to break your tool. And so that happens a fair amount. Somebody will go fuzz and they'll find some. I love to fix. We've had that happen with Binary Ninja where we fixed the bug mid-CTF. So if you ever release a CTF challenge that actually crashes us, quite often we'll fix it in the middle of the CTF just because I think it's hilarious. Because we release like rolling updates like frequently. So yeah.
Thank you so much.
You're welcome. Good question. Anybody else? Yes.
Thank you so much for your talk, Jordan. You mentioned that the AES instruction in x86 and how in Binary Ninja you decide to use it as a single
An intrinsic, we call it. Yeah.
for like clarity, and whereas for example Ghidra uses like the full.
I don't know if they do it for AES,
okay.
but for the vector instructions they did.
Correct.
Yeah.
Are there any like situations where Binary Ninja does the same way Ghidra like does for vector instructions, where you show the whole thing, and in which cases would you use it for readability?
It's a good question. Shusheng might actually know the answer better than I do if you can think of one off the top of your head.
So I'm the developer that writes all of the code that deals with the x86. I don't think we actually, partially because we use.
Well, like any of the weird ones, yeah. So the answer is like all of the AES instructions, all the vector instructions, we treat as intrinsics.
Yeah, because we pretty much believe that the readability is better if we just use an intrinsic to handle that rather than trying to expand the semantics of the instruction. Now that is the official answer. My own answer is if you guys force me to leave every instruction, I wouldn't be able to do anything else. Yep.
Yeah, that's a good question. And again, from a program analysis perspective, though, if you purely want automation, you might really want that because there may be more you can do. You know, if somebody's like encrypting a pointer, decrypting it, or doing some vectorized operations on it, you're going to miss control flow, code flow, which again, that goes back to the this is all impossible part. You can always make things harder. Yeah. You're welcome. Yeah. Any other questions? All right. Thanks, everybody. Appreciate it.